Good morning, everyone. We are from Group 2B, and today we are excited to present our topic, the development of methanol production. Our presentation will cover the fundamental aspect of methanol production, detailing the key processes involved, the necessary calculation, and the overall plant design. Before we dive into the specifics, I'd like to introduce the dedicated team behind this research. My name is Muhammad Najmuddin. I am joined by Raakesh, Ariff, uh, Raja Nur Alya, and Anish Insyirah.
So basically for introduction we have energy balance and also mass balance. Okay, so for energy balance it basically monitors the heat and the work interactions. So the purpose of energy balance is basically to improve process efficiency and reduce potential heat loss. So for mass balance, it helps to track material flow. Okay, and for that purpose it minimizes waste and maximizes the yield, and also accounts for inputs, reactions and outputs. And the core principles is basically relies on fundamental principles of designing, optimizing and operation of industrial process. Okay, for PFD, which is process flow diagram, visual representation of material and energy movement in a system. Okay, that's PFD basically. And the purpose is basically is helps to identify critical unit operations, ensure efficient component integration.
Okay, so I'll be presenting of our process flow diagram of our methanol production, where we aim to produce around 1.7 million metric ton per year of methanol, where it undergo processes such as steam reforming and methanol synthesis. So for here, as you can see, our feed consists of methane and steam, where it undergoes the first reaction with syngas production, which occurs in the first reactor. Then it is cooled down in a condenser where water is removed. It is then enters the second reactor, which is R102, where it undergoes photosynthesis, where it produces a low purity version of a methanol. Then to get the desired product of 97%, we basically put it through two distillation columns, where it will basically allow our purity of metal to increase to 97%. Then it is then stored in a storage tank for further notice. And also on the other side, on the side, you can see the amount of unit operations that are used in this process. Thank you.
The system first converts methane and steam into syngas in reformer R101, then cools it in D101 to remove water. The syngas gets preheated in H101 before methanol synthesized in reactor R102. Unreacted gas recycled back while impurities purged out. Finally, the mixture gets purified in D103 to yield 97% methanol for storage in T101 with water removed as waste. The entire process optimizes efficiency through heat recovery and gas recycle.
To accurately perform the mass and energy balance calculation for a methanol production process, it was essential to establish a set of key assumptions. These assumptions, as detailed in Table 3.1 for material balance and also in Table 3.4 for energy balance, are critical for developing a robust and reliable model. We've carefully justified each assumptions by referring to established industry practices, relevant academic literature, and in some cases by referring to symmetry SLB, mass fraction data, for specific stream compositions. This meticulous approach allows us to confidently determine the mass flow and energy requirement throughout the process.
So thank you, Najmuddin. Now we proceed the presentation on the calculation mass balance of the reactive component. So we choose the steam reformer. So we need to find the extent of the reaction. With the extent of the reaction, we can calculate the mole flow rate of the each component. For the mass balance non-reactive components, we need to know the overall balance equation and also methanol balance equations. With these equations, we can find the mass flow rate for the inlet and the outlets. For the energy balance of the reactive components, we get the data H89717452.6.7 kJ per hour. However, for the energy balance of the non-reactive components, which purification methanol, we we can calculate it from inlet, outlet enthalpy table. So we can get the delta H, which is negative 5959,35234.2 kJ per hours. Now we will pass it to the Najmuddin.
So, in conclusion, our analysis underscores the effectiveness of the Allergy megamethanol process as a proven and highly efficient technology for large-scale methanol production. The success of this process hinges on the precise application of mass and energy balance principles and advanced process design, enabling the efficient production of high quality and high purity of methanol while minimizing the natural gas consumption. Looking ahead, with rising global demand, the future methanol synthesis will undoubtedly be shaped by ongoing advancement in catalyst development, process intensification, and the integration of renewable energy sources, driving us towards a more sustainable chemical industry. That is it for us from Group 2B. Thank you.